Acid-base titration, example 4. Answer the following questions regarding a 0.05 liter solution of a 0.1 molar solution of a weak acid, symbolized Hz, with an acid dissociation constant, K sub A, of 7.20 times 10 to the negative 4. The solution is titrated with a 0.15 moles per liter or molar lithium hydroxide. The pH at the equivalence point is approximately 8.2. Part A. Calculate the volume of base needed to reach the equivalence point. All right, what do we do? I've been given the concentration of a weak acid. Let's let me calculate the number of moles of that acid using the formula volume times concentration. Each acid molecule donates one hydrogen ion. Base is needed to neutralize 1 mole of acid, so the number of moles of base needed to reach the equivalent point is equal to the number of moles of acid. Now, using the concentration of the base that we know, I can solve for the volume of base required. Volume equals molarity divided by concentration. And that wraps up Part A. Part B is calculate the pKa for that weak acid. Well, we're given the Ka. I just needed the Ka. And once I have that, I just take the negative log. So pKa equals the negative log of the acid dissociation constant. Quick and simple. Then we ask ourselves, does this pKa make sense for a weak acid? Well, it should fall somewhere between 3 and 7. Part C, determine the pH of the original weak acid solution before any titration even begins. Okay, so what's going on before the titration starts? The weak acid partially dissociates in water. This creates an equilibrium between the undissociated acid, its conjugate base, and hydronium ions. So let's use the Rice table to model this. The initial concentration of the weak acid is known. There's essentially no hydronium, or H3O+, and no conjugate base to start with. As the reaction or the shifting progresses, the concentration of acid decreases by some amount, we'll call X, while the concentrations of the conjugate base and the hydronium ion each increase by X. The expression for acid dissociation constant, Ka, is the products, conjugate base and hydronium ion concentrations, divided by the acid concentration. Substituting the terms X, if there is a small x compared to the initial concentration, we can simplify that expression, and this avoids using the quadratic formula. So solving for x gives the hydronium concentration, at equilibrium. From there, the pH can be found simply by taking the negative log of that value. This gives us an initial point on our titration curve as well as the pH before any base has been added. If we want to double check, we can also use a shortcut. pH is 1/2 the difference between the negative log of the acid concentration and the pKa, or the negative log of the acid dissociation constant Ka. Plugging it in gives us a similar answer. So it's nice to verify the two methods, that it gives us the same results. Memorize this shortcut, it could be very useful. Part D is our titration curve. Let's build this step by step. It starts at the pH that we just calculated, the weak acid's initial pH before any base is added. As base is added, the pH rises gradually, especially during the buffering region. At the half equivalence point, half of the acid has been neutralized. At this exact volume, the acid concentration is equal to the conjugate base concentration. and that causes pH to be equal to pKa. After the equivalence point, excess strong base, at the equivalence point, all the acid is neutralized. Because we're titrating a weak acid with a strong base, the solution now only contains the conjugate base, so the pH will be above 7, somewhere in the basic range. After the equivalence point, excess strong base dominates and the pH climbs quickly before leveling off near the top of the curve. Don't forget that this curve is not a straight one. This is a shallow rise at the beginning, a buffering plateau, a steep vertical jump at equivalence, and then a leveling off as more base is added. And that's it, a full titration curve from start to finish. All right, did we hit all the parts in this example? We hit all the parts in this problem. Heck yeah, let's go.